universal set. So the intersection will be the subset. Okay. Now writing one more line, X belongs to A union B and X belongs to A intersection B complement means X does not belong to A intersection B. Okay. Being in the complement means being not in the set. The complement is outside of the set. Now you see what this structure tells you. X belongs to a set and X does not belong to another set, which means X belongs to their difference, A union B minus A intersection B. So if you recall, we started by assuming X belongs to A minus B union B minus A, and then by applying all these arguments we have arrived at this. Hence A minus B union B minus A is a subset of A union B minus B union A. Now we have to prove the opposite. Okay, since the proof is rather complicated, I will not leave it. Okay, so let me do it once more. Once more means let me prove the other containment also. So now what I do, I have to prove that this is a subset of this. So I start by taking an element in this, A union B minus A intersection B. It implies, same as usual, Y belongs to A union B and Y does not belong to A intersection B. I think it will just simply follow the same arguments in the reverse order. That's what I think. Y belongs to A or Y belongs to B, but we while proving this one, we along the way we came across a universal set which we took its intersection with some other set. So universal set was lost somewhere in the argument. So do we have to bring the universal set back? That is, do we have to literally carry out this part in the reverse order of the previous one? That's what I don't know at this point. Let us see what happens. Okay, now Y does not belong to A intersection B means same. Y belongs to its complement. So far things are just like how we had them previously. But now, maybe they are going to change. Or Y belongs to B. This we cannot do anything. We have already written what can be written here. Here, however, we can simplify or change the situation. Again, we are using De Morgan's law. In its place, we write A prime union B prime. A complement union B complement. Okay. Now this stays the same. Y belongs to B. And Y belongs to A complement or Y belongs to B complement. Now here, just like how we applied the distributive law twice or 4 times, I don't know how many times. So here also we have to do that once more. So Y belongs to A or Y belongs to B and y belongs to A complement. This is one thing I need space, and or. See, these things are very confusing if you are not paying attention while carrying out these things. As there will be some simple mistake and that will make the whole thing obsolete. Okay, y belongs to A or y belongs to B and y belongs to B complement. So I can wrap this much up and start from here again, continue from here. So again, similarly, I apply commutative law, y belongs to A complement and y belongs to A or y belongs to B. Or instead of and, now we have or. Here also I use the commutative law, and y belongs to A or y belongs to B. Now I have to again apply distributive law twice. So y belongs to, this implies y belongs to A complement and y belongs to A, or y belongs to A complement and y belongs to B. Or similarly, on that one we apply distributive law, y belongs to B complement and y belongs to A, or y belongs to B complement and y belongs to B. Okay, now we have and we have the same elements, so y belongs to A complement intersection A, or y, okay, now this can also be written like y belongs to B and y belongs to A complement means y does not belong to A. Or this much. So this tells you y belongs to B complement and y belongs to A. This can be written as y belongs to A and y does not belong to B. Or we have and, so just like that one, B complement intersection B. Okay. Continuing from here, this implies. Now, if you recall the properties of complements, any set and its complement have no elements in common. That is because this is our universal set. This is A. A complement is just what is not in A. So clearly from the definition, their intersection is empty. So this means y belongs to the empty set. Or now you look at this, y belongs to B and y does not belong to A, which means y belongs to B minus A. or here y belongs to A and y does not belong to B, which means y belongs to A minus B. Or similarly here y belongs to the empty set. Okay, now we have or, so we can write y belongs to empty set union B minus A, or y belongs to A minus B union empty set. And if you remember the properties of union, if you take the union of any set with the empty set, you get the set back. So this means y belongs to B minus A, or y belongs to, similarly here also, A minus B, which can also be written using commutativity of disjunction. Y belongs to A minus B, or y belongs to B minus A. This implies y belongs to A minus B union B minus A. So we have proved that whenever y is in A union B minus A intersection B, then y is here, which means that this is a subset of this. We already had the other containment, so these two are equal. That is, this is equal to A union B minus A intersection B. So this is what we wanted to prove. By definition, this much is the symmetric difference of A and B. Okay, so that's how we have got this. So our guess is actually correct. Most of the guesses we make from a Venn diagram turn out to be true. Now you can also see one more thing immediately from the definition itself. Don't have to put that much effort. Is that B delta A equal to B minus A union A minus B is also equal to this. That means B delta A is equal to A delta B, or symmetric difference is commutative. Okay, A delta B is equal to B delta A. It follows immediately from the definition of symmetric difference. Symmetric difference is associative also. If we have three sets A, B and C, A delta B delta C equals A delta B delta C. This, however, its proof is extremely complicated, or I don't know whether I should say complicated or not, since that is a subjective term, but it is lengthy. I will prove this at one point, but right now we are leaving this like this. We just take it like this, that this is true and it is given to us, because symmetric difference will not appear in many places. It will appear only once when you study ring theory, and it is the classic example of something called a Boolean ring. Okay, in higher algebra there is a subject called ring theory. There this symmetric difference arises in an example of a Boolean ring. We will see what these things are in future. There are some One more property is there which involves this delta and intersection. Intersection distributes over symmetric difference. A intersection B delta. This is not very difficult to prove. Not as difficult as this one. This one is quite difficult. Delta A intersection C. See, the difficulty of this comes from the fact, okay, how difficult a given identity in set theory will be, that can be gauged somewhat by looking at the Venn diagram of the set. There are three sets involved, right? A, B and C. Now, what have we learned just now? If you want to perform symmetric difference of two sets, you take their union and remove the intersection from that union. Whatever is left is the symmetric difference. So if you try to draw the Venn diagram of this set, this one, then first you have symmetric difference of B and C, which means this is the set B, this is the set C. So the symmetric difference is B union C minus B intersection C. So this much is the symmetric difference of B and C. This and this. That is C minus B. This the lower one is B minus C. Now with this set, we are taking the symmetric difference of A, which means I take the union of this set along with A and subtract the common part between A and B delta C. So if I draw the union, how would the union look like? The entirety of A will be there. Okay, so that is A, and this is B delta C, excluding the common part. Now, what is the common part between A and B delta C? This much and this much. Okay. So if I have to remove that, that means so actually this is my A delta B delta C. What is it? It has the elements which are only in A or only in B or only in C or in all the three of them. This is my A delta B delta C. Now if I try to draw the Venn diagram for this one, let us go through this also, since we are doing in a similar manner A, B, C. Now I have A delta B. Now A delta B is this much. Things that are only in A or things that are only in B. Okay. Along with that, I take C. First, I take their union. Then I remove the common part. So, common part is this much. And this much. So you see that we get the same set. So from the Venn diagram, it seems like they should be equal. Of course, this is not a proof. The proof has to be carried out using the definitions of symmetric difference, not Venn diagram. But from the Venn diagram, we can see that this should be true. Similarly, you can try to see that this is also true. Okay, so these properties I will not prove. Will not prove means at some point I will prove, but it's not now. It's in future. There are some other quite trivial properties, or one property, which is that the symmetric difference of a set with itself is empty set, because this is A minus A union A minus A, which is empty set union empty set, which is equal to empty set. Okay, so this is one. Another operation other than the four that we have already come across, it occurs much less frequently, but nonetheless it's also there. Okay. Now before we proceed and solve some problems involving set theory, we have to prove three fundamental things which we have left out, and which are these. For sets A and B, we have number one, for finite sets, for finite sets, we have cardinality of A cross B is nothing but cardinality of A times cardinality of B. Number two, cardinality of A union B is equal to cardinality of A plus cardinality of B minus cardinality of A intersection B. And number three, this one we have already seen, but we haven't proved it. Cardinality of power set of A is 2 to the power cardinality of A. Okay, these three things we have to prove, and they are very helpful, especially this one, the second one. It is used again and again in many problems involving set theory. So let us prove the first one first. Now before we do so, I want to tell something about the principle of mathematical induction. There is something in mathematics called mathematical induction. In fact, without this principle, mathematics would not even start. Okay, without this principle, we basically cannot do anything. Why? That you will realize as we go deeper and deeper. Okay, so what this principle says, it's not very complicated, it's rather easy. Let A be a subset of N, the set of natural numbers, with the following properties. Number 1. Okay, but I must make sure what N means. Let us from now on make it a convention that for us N will mean this set. We are not going to say this again and again. For us, the set of natural numbers has 0. Okay, it's not the set of positive integers, it's the set of non-negative integers which are not negative. So N has 0. So number 1, 0 belongs to A. So I have considered a set A in N means it's a subset of N. Okay, I should have written like this, otherwise it would be a proper subset. So A is any subset of N satisfying two properties. One of them is that the element 0 must be in A. The second one is if N belongs to A, then N plus 1 belongs to A. Okay, so these are two properties that the subset A of N satisfies. Then if this is the case, then A is actually equal to N. This is the principle of mathematical induction. What it says is that you have a subset A of N. So this is your N, right? It goes like this. So A is here somewhere. A is a subset. It may or may not be equal to, and we don't know in advance. In fact, that's what we are concluding as the result, as the principle. So A is any subset, but what is given to you? A contains 0, and whenever there is an element in A, its next element n plus 1 is also in A. For example, since 0 is in A, so 0 plus 1 equal to 1 is also in A. Since 1 is in A, 1 plus 1 equal to 2 is also in A. Like that, you can see roughly that all the elements will eventually be in A. That's why A is equal to N. But that is not a proof, okay? Now this principle is taken as it is, without any proof. It is assumed that this holds true, and then mathematics is developed using this. And this principle is rather useful in proving statements which involve natural numbers in a very nice way. So we are going to prove this one using this principle of mathematical induction, and we will see actually how this principle helps us prove something like this. Okay, so let us start the proof. So I hope you understand the principle. You take a subset of natural numbers which satisfies two properties. The first, the element 0 is there in that subset, and whenever something is there, then the next one is also there. Then that subset must be the whole set of natural numbers. It's something like this. You put a series of dominoes. You push one. Okay. You push one over, that knocks the next one. The next one then falls over, and that knocks the next one. and the effect goes like that. All the dominoes eventually fall. It is something like that. This is the first push, and once this has been pushed, then it pushes the next one, 1. Then that pushes the next one, 2. So all the things fall in A. Okay, so that is the principle of mathematical induction. Now this principle has a stronger form also. Let me state that one also so that I will have them, both of them at once. What is it called? The strong induction principle. The strong induction principle. It's somewhat like the original one, but slightly different. Again, we start off with a subset of the set of natural numbers. Let A be a subset of n with the following properties. Number one is same. 0 belongs to A. Okay. Number 2 is slightly different. If 0, 1, etc. up to some k, some number k, some natural number k, if all of them belong to A, then k plus 1 belongs to A. So these are the two properties that the subset A satisfies. Then the conclusion is same. A is equal to n. So instead of just assuming that k belongs to A implies k plus 1 belongs to A. See, if then means implies, right? This statement is also an implication. We are assuming an implication where the hypothesis is stronger. Instead of k belonging to A, we are assuming that all the natural numbers starting from 0 all the way through k, all of them belong to A, then A plus 1 belongs to A. If these two properties are satisfied by A, then A has to be equal to n. Okay. Now once we assume the original principle, the strong principle is actually a corollary. It can be proved from that one. Anyway, right now we don't need such proofs and things. We just need to use these principles to prove something else, namely this one. Okay. Proof. Now, if we are going to apply induction in a proof, we mention that. Okay, we apply induction on, say, cardinality of A. Why? What does that mean? It means that, sorry, the cardinality of A is a natural number. Always remember that. Cardinality of A means what? The number of elements in A. Okay, and that number may be 0, 1, 2, etc. And because it is given that A is finite, that's why the cardinality is coming into question. Because for infinite sets, we have not defined cardinality. Although there are, there is a concept of cardinality for infinite sets also, but that is a higher concept which is way beyond our current stage, the level at which we are right now, it's way beyond that. So we apply induction on A. But what does that mean? It means that, see, what we are trying to do here, we are trying to show that this statement is true for all values of this cardinality of A. And cardinality of A can take these values, it can either be 0 or 1 or 2, etc. It can be any of these. So we want to prove that it is true for all of them. So actually what we do, the strategy of the proof is like this. We consider a set S. What is S? S is the set of those natural numbers such that for all finite sets A and B, such that cardinality of A is equal to K. Look at this set carefully. Okay, what is this set? It is the set of all natural numbers n such that what? Such that this is true whenever A has K elements. Now, it means that, for example, if A has 0 element, that is if A is empty set, and this property turns out to be true when A is empty, then 0 belongs to S.